Hi, this is Dr. S and this is video 15 in my series on reaction rates for Year 13 A-Level Chemistry. In this video we'll look at the logarithmic form of the Arrhenius equation. So in the previous videos we've looked at the Arrhenius equation, which is K equals A e to the power of minus EA over RT. And in the last video we looked at how to calculate the rate constant if we were given all the other numbers. It becomes problematic if we want to calculate something else in here, because it's quite hard, if you don't know your advanced mathematics, to rearrange this equation. So we have to become familiar with the logarithmic form. Now you don't have to actually derive this form. A-level mathematicians will be able to do this, but if you don't do maths, it's not a problem because you will be given this equation. But the inverse of an e is an ln, a natural log. So if you perform a natural log function on all of these, what you end up with is ln k, ln is natural log, equals ln a, I'll leave it as a plus for now, plus minus ea over rt. So what we've done is we've got rid of the e, which means that this, which was a power, now comes in line. So we can now do a bit more rearranging with this. Of course we've got a plus and a minus. Now actually the form you will probably see on your data sheet actually looks more like this. ln k equals minus ea over rt plus ln a. So the minus bits come to the front and the plus has gone over there. Now there's a reason that it's rearranged like this. That's because this is putting it more into the form like a graphical form of a straight line graph, which is y equals mx plus c. That's the general formula for a straight line graph. And what we'll find is that if we split this up into two terms, so we have an m term and an x term, then we can do some calculations based on a graph. So just to remind you, y is the y-axis, x is the x-axis, m is the gradient, and c is the y-intercept. So how we split this up is we take our minus ea over rt and we split it into m and x. Well, x has to be something we can measure. Temperature is the easiest thing to measure, but temperature is on the bottom of this term here. So we're going to split it up into m and x, where x is 1 over t, and m is the rest of it, so minus ea over r. So that now is m times x plus c, which is ln a, and y is ln k. So what that means is, if we have our y term and our x term, we can create a graph where our y-axis is ln k and my x-axis is 1 over t. Now the reason I've drawn it like this is because you often get graphs like this where it spans over the zero, spans over the x-axis. So now what we need to look at is how we get our m and our c. Well, in my next video I'll actually perform one of these graphs. But on my sketch graph, what I'll do is just draw a line like that. You'll get a straight line graph for this because it follows the equation for a straight line graph. And then we can look at the important parts of this graph. So here's the y-intercept. So that there will be the value of ln a. In the next video I'll show you how to then use that to find out a. We then have our gradient. The gradient is m, so that is minus ea over r. And if you notice, it's minus ea over r. Well, activation energy has to be positive because it's the minimum energy needed. You can't have a negative activation energy. So if the gradient is minus ea over r, you will always get a negative gradient on one of these Arrhenius graphs. Okay, now this bit is quite complicated, matching up the Arrhenius equation, which is quite hard anyway, to the equation for a straight line graph. A lot of students struggle with it. So please don't be worried if you find it difficult, and bear in mind that these will be given to you. These equations will be given to you. So you don't have to remember them, you don't have to manipulate them. What you do have to do is be able to create a graph and then evaluate the graph from it. So that's what we'll do in our next video. I'll see you then.